large. It's possible that every horizontal line segment intersects every vertical line segment. For instance, if all the horizontal lines go from this end to that end, and all the vertical line segments go from top to bottom, you'll get lots and lots of intersections, and your job is to report all of them. Or it might be simply, as I said before, that there are none or very few. So what you would like to do is to design an algorithm where the time you spend is sensitive to how many intersections there are. Okay? Of course, you have to do some basic work, but beyond that, you don't want to spend too much time if there aren't very many intersections. And one of the things that you need to understand here is that, let's say for the sake of argument that you have n vertical line segments and you have m horizontal line segments. In general, there could be this many different intersections, right? As I said, every line segment, every vertical and horizontal line segment might intersect. By the way, we are assuming here that two horizontal line segments don't intersect, although theoretically they could. One could sit on top of each other, but we're ignoring those. Okay? You could take that into account if you want, but either way, this is actually a quadratic number. If you assume that both the number of horizontal and vertical line segments are the same, if they're both n, then you could have n squared intersections. So the number of intersections can be as large as quadratic, or it could be as large as 0, right? And you want the time that you spend to be proportional to the number of intersections you have. If it is small, you want to spend a small amount of time. If it's large, then it's okay to spend a lot of time. Okay? And the question is, how do we do it in this output sensitive way? In order to understand this, we're going to first start with understanding a basic data structure. I'm just trying to make sure that everyone is on the same page in terms of understanding this data structure. The basic data structure we're going to assume is what is called as a balanced binary tree structure. Balanced binary search tree, sorry. A balanced binary search tree is a data structure. It's actually a dynamic data structure. It's a dynamic data structure because it assumes that the data it's storing is constantly changing. It's assuming that things are constantly being inserted into it, things are constantly being deleted from it, and there are some search operations you perform. So it assumes that you have three basic operations: insert, delete, and search. Okay? So you don't know how many things are going to get inserted, you don't know how many things are going to get deleted, but the search is all three operations should happen efficiently. And what does efficiently mean? If there are n items in this data structure, you want each of these operations to run in log of n time. Okay? So if there are n items here at any given time, you want each of these operations to run in log of n time. Such a data structure is considered efficient. In general, we can prove that you can't do search faster than log n. There are all these lower bounds we've talked about, and you've probably seen in various classes, but all that is secondary. Since this is the best you can do, at least even though this is dynamic, things are constantly changing, you want to be able to make sure that these operations are handled quickly. And this balanced binary search tree data structure actually manages to do so. So it achieves log n for each of these operations. And a well-known balanced binary search tree structure is called the red-black tree. So if you use something called a red-black tree, then you will achieve, it's a kind of balanced binary search tree structure, and it achieves log n time complexity for each of these operations. Yeah.
So a red-black tree is like a implementation?
It's an implementation of a balanced binary search tree structure. Okay. So it actually is a binary, it implements a binary search tree, it keeps things balanced. All those details you can learn in some other class. You can, I think this is taught even in your data structures class, or you can go to the algorithms class, will tell you more details. Java allows this, I think even Python code should be readily available, but you can easily find the code for this and implement it. Which means that for any problem, you can simply take code that's available on the internet and build such a thing. Now, this kind of data structure is useful because it's now a tool to solve different problems. In particular, I'm going to show you how it helps to solve this problem here. Okay? Any questions so far about this data structure or anything you've seen so far? Okay, no questions. All right, good. So yeah, this, as I said, is the important piece. Your data structure allows for this to happen, as long as the number of items never goes beyond n, or big O of n. This time complexity is going to be log of n. Okay, this is what we need to know. Now, let's forget about this for a bit. All we need to keep in our head is, oh yeah, there's this data structure that allows for inserts and deletes efficiently. Let's see how we're going to use this over here. In order to solve this problem, as I said last time, we're going to use something called a line sweep algorithm or a line sweep technique. What is a line sweep technique? You take this red line that I've shown here, start it at the left end of the picture, and you sweep it across this and until it crosses all the line segments and goes off to the right. Along its path, it's going to encounter things that are in the picture, in particular horizontal and vertical line segments. And as it sees this, it needs to report all the intersections that it sees, that it spots. And if it doesn't spot any, it's going to just say, oh yeah, I didn't see any. So this vertical line segment is going to do the job of making sure that as it crosses the intersection, it reports it if one exists. So if it crosses, if it goes past this point, it should report that particular intersection. And then when it goes even further, when it comes here, it should report that particular intersection. And that's its job. Okay? Now here is the nice trick that we're going to employ. What we're going to do is, if we kept all the horizontal line segments if we, one possible way to solve this problem is just take all your horizontal line segments, compare it against all your vertical line segments, and then report whichever ones intersect. That's easy. It's easy to figure out whether a given horizontal line segment intersects with a given vertical line segment. How do you figure this out? Well, there are simple techniques. You have to make sure that the y-coordinate of this horizontal guy is between the y-coordinates of the endpoints of this, and you also have to make sure that the x-coordinate of this vertical line segment is between the endpoints of this. Right? Pretty easy to figure this out, because here I would have x1, y1. Sorry, let me call this x11, y1, and this would be x12, y1, right? Because the y-coordinate is the same for both these points, right? And then for this guy here, let's assume that its x-coordinate is going to be the same for the two endpoints. So let's call this x2 comma y2 1 and x2 comma y2 2. All right. So what you see here is that both these points have the same x coordinate, both these points have the same y coordinate, right? And as I said before, you want y1, if they are to intersect, you want y1 to be in between y21 and y22, right? So it should be something like this, right? And you want, what's the second condition? Yeah? Yes? x11, x2, x12, right? So if both these conditions are satisfied, they're going to intersect, otherwise they won't. Pretty easy to verify this. So why can't I just do this for every possible horizontal and vertical line segment? I could report everything. The problem with that is that you're going to end up spending time that's proportional to the number of horizontal line segments times the number of vertical line segments. And as I said before, this is going to give you quadratic time algorithms. That's going to be very very inefficient. If I have 1,000 horizontal line segments and 1,000 vertical line segments, I'm going to do 1,000,000 such computations, right? That's too expensive because it's possible that the number of intersections are only 5, right? So we have to do something that's a little more efficient, and so we are going to use this data structure. And here's how this goes. And actually there are various ways of doing it. What we can do is as the horizontal, as this red line sweeps, we'll figure out which horizontal lines are active at any given time. Okay. At this particular point, there's this horizontal line, this one, that one's actually, that one is also still active, and there are 2 more at top. So there are 5 horizontal line segments that are active at that particular x coordinate. We're going to maintain a balanced binary search tree with those 5 horizontal line segments, but we're going to save them according to their y coordinates. Okay, the key value that you'll use to store here is going to be their y coordinates. So when this next line segment gets encountered, this vertical line segment, we are going to check whether the vertical coordinates of this point intersects any of those horizontal line segments. And it's going to be a lot easier because what we are storing at that time is the horizontal line segments that are active. So for instance, let me draw that picture again. Let's say we have these horizontal line segments, and here is our vertical line sweep. This is what it looks like at any given time. This is the sweeping line that's sweeping to the right, and those are the active horizontal line segments. And each one has a y coordinate. We'll call this, let's say, y1, y2, y3, y4, and y5. Remember, a horizontal line segment has only one y coordinate, right? We're going to take all those 5 and we're going to put it in our red-black tree. So the red-black tree is only going to have these 5 values. So it's only going to have y1, y2, y3, y4, and y5. How they're organized in that red-black tree is not our business. That's the job of the red-black tree. It maintains this. Okay? And now let's say we encounter a vertical line segment. So let's say that we encounter this vertical line segment. And remember, vertical line segments have a lower endpoint and an upper endpoint. So there's a lower y coordinate and an upper y coordinate. So let's call this YL and YU for lower and upper. Our job is to figure out all the horizontal lines it intersects between YL and YU. Okay, so how do we do that? What we're going to do is search for YL in this data structure. Okay, when we do that search, it will tell us between which two values of y coordinates it falls. In this case, YL falls between y4 and y5, right? So when we do a search with YL, it'll tell us that it's between y4 and y5. So it's somewhere in between this. That's where YL is. Okay. Now if YU also falls between y4 and y5, how many intersections are you going to have? 0, right? Because both are right here between y4 and y5. So it's not going to intersect anything. So I'm going to now search for YU in the same structure, and it's going to tell me that it's between y2 and y3. By the way, it's better to write this so that it's in sorted order. Even though it's a red-black tree, it's going to be organized in some manner. So remember, y5 is the smallest, then we have y4, then y3, then y2, and then y1, right? So somehow it organizes this and it knows that it's in that order. And when you search for YL, it'll tell you that YL lies somewhere in between this. Now I'm going to search for YU, and it'll tell me that it's between 2 and 3. So YU is somewhere there. So immediately I know that anything between YL and YU, those horizontal line segments have to intersect this vertical line segment, which means that Y4 and Y3 are going to give us intersections with that vertical line segment. Okay, so I can just simply go through the red-black tree and figure out which ones lie between YL and YU, and I'll report all those. So I may have to add an extra operation here that says, let me give you two values, give me all the values in the red-black tree that are between these two values. And that's a simple operation. And over here, you'll end up reporting all your intersections. And the intersections are easy because the vertical line segment has an x coordinate, and the horizontal line segments have a y coordinate. And so those are going to be our intersection points. So the intersection points are going to be the x coordinate of the vertical line segment and the y coordinates y3 and y4. Is that clear? So whatever is the x coordinate of this guy here, in this case it'll be x, let's call it just x. The point of intersection is going to be x, y3 and x, y4. I see some blank stares. So ask me questions, guys. Make sense? Now, the time complexity of reporting this turns out to be not quite log n, but it's actually log n plus the number of intersections. So if YL is to the left is smaller than Y5 and YU is larger than Y1, it has to report all of these. So there could be a lot of intersections. So you can't do that in log n time. Or it could be that both of them end up being between Y3 and Y4, in which case you get no intersections. So the time complexity turns out to be exactly log n plus the number of intersections, which is quite nice, right?
How do you keep track of the active lines?
Yeah, I'll tell you that in a second. So this is the key step. All it says is, at any given time, if you know what that vertical sweep, the x-coordinate of the vertical sweep is, I can figure this out. So we know how to report intersections at any given time. The next thing is to answer what Rukman was asking, namely, how do you get this line to move, and how do we keep track of all the horizontal line segments? Because horizontal line segments that are active will continuously change, right? So this is where we are going to use what is called as event-based algorithms. Now, the the vertical line segment, red line that sweeps from one end to the other, starts over here and ends over here. We will take, and what is useful to know is that the only intersections are going to be at the x-coordinate of the vertical line segments, because you don't have to worry about two horizontal line segments intersecting. So as long as you go and stop this vertical line sweep at the x-coordinate of all these vertical line segments, we can report all the intersections we need. So when we are here, we're going to do the checking and we'll report those three. When we are here, we'll report this one. When we are here, we'll report that one. When we are here, we'll report nothing. When we are here, we'll report two of those. Here one, here one, here three, here one, there one, there one, and here 0. So as the vertical line segment sweeps, we'll end up reporting all these intersections. But at each of these stops, we're going to spend at least a log n amount of time. So it's going to be log n plus the number of intersections. And so the number of stops we have is the number of vertical line segments. We'll assume it's n. And so we're going to spend n times log n plus the total number of intersections. So the total time complexity turns out to be n log n plus the number of intersections that we actually report, which is whatever that number is. Yeah, you got it. Okay. So the next question is, how are we going to maintain the horizontal line segments? And this is where we use this plane sweep technique, and we use what's called as an event queue. This event-based technique is quite powerful because, don't read this now, we are going to assume that we already know that the events are only at the x-coordinates of vertical line segments. So we'll just build a event queue that has, actually no, let me restart it and say it differently. We are going to create a queue which is going to be a sorted list of the following things. A sorted x-coordinates, a sorted list of, fine. In particular, we'll have x-coordinates of vertical line segments. No, it's a queue. And an x-coordinates of endpoints of horizontal line segments. Okay, so all the horizontal line segments will contribute two values, its left endpoint and the right endpoint, and all the vertical line segments will contribute one value, and that's its x-coordinate. All that, we're going to put it into a queue. We're going to call this the event queue. And it turns out that we have to do some work every time one of these one of these x coordinates become the place where the line sweep stops. So the line sweep, the vertical line, the red line, will make stops at each of these places. So think of it as a train that goes from this end to that end. Along the way, it's going to make stops at these places. And at each of these places, it's going to do some work. And the question is, what is that work? Well, at each point, it's going to maintain all the horizontal line segments that are active. That's what we're going to assume. So therefore, when it hits the x coordinate of a vertical line segment, it simply does what I just described here and reports all the intersections. So the key thing is what happens with the x coordinates of the horizontal line segments. At that point, either it's going to be a left endpoint or a right endpoint, right? Because we're throwing into this queue x coordinates of both the left endpoint as well as the right endpoint of a horizontal line segment. So here is let me go back to the previous picture. Each of these horizontal line segments will have a start point and an end point, a left endpoint and a right endpoint. So this point is going to be in the queue, and so is this point. When we hit this point, we have to do some work. When we hit this point, we have to do some work. What is the work that we are doing? It's actually very simple. When we get here, a new horizontal line segment has become active. So we insert it into our data structure. When we get here, the horizontal line segment is not active anymore, so we delete it from our data structure. And both these operations are allowed with this red-black tree structure. So now we put together all the pieces. The pieces are very, very simple. We have a queue, an event queue that contains all the x coordinates. These are the only interesting x coordinates that are of interest to us. Either it's the x coordinate of a vertical line segment, or it's the beginning of a horizontal line segment, or the end of a horizontal line segment. These are the only three kinds of events we are interested in. Anything else is worthless because there are never going to be any intersections at any other x coordinate, right? So this is the event queue that's on the side. Then we are going to maintain a second data structure that contains the active horizontal line segments and their y coordinates. So let me write that here. This is going to be active horizontal line segments. All right. When the vertical line sweep is over here, we don't have any line segments that are active, so this is simply going to be an empty data structure. Then we're going to take, the line segment is going to stop at all these x coordinates that are here. These are going to be sorted, so we know in what order to process the events. So we'll go to the first event. If that first event is a left-hand point of a horizontal line segment, we're going to insert it into the queue. If the next event we have is the end point of a horizontal line segment, we'll remove it from here. If it's a vertical line segment instead, we'll do the job of reporting anything that it intersects. And that intersection is the x coordinate, we're going to figure out what the range of y coordinates the vertical line segment has. Look over here, find all the horizontal line segments it would intersect and report those. So 3 different events and 3 different kinds of tasks. So that gives us a very simple algorithm. Well, this is just a description of all that I just told you. This also I told you. So here is the algorithm. I know it's not very, very readable, but you can see here the input bunch of vertical line segments and a bunch of horizontal line segments. We're assuming m vertical and n horizontal. and the output is all the intersections. The first step is to sort all the x coordinates in increasing order. And the only x coordinates that are relevant are the left endpoint and right endpoint of horizontal guys and the x coordinate of a vertical line segment. You take all of those and put it into your event queue. Then we start this data structure. That data structure is not quite made clear here. Think of your data structure as an empty data structure to start with. Then it says until you get to the end of the queue, end of the event queue, so you're going from left to right. You look at the first endpoint that comes out of the queue, the next thing on your sorted list, right? And you check whether it's a left endpoint, right endpoint, or a vertical line. If it's a left endpoint, you insert a new horizontal line into your data structure. If it's a right endpoint, you remove it from the data structure. That's the active line segments, because if you're hitting the left endpoint, it's now a new horizontal line that's becoming active. If you hit the right endpoint, one of the active line segments is now inactive. And then otherwise, it must be the x coordinate of a vertical line, in which case we do what's called a one-dimensional range query. We're asking between the two y coordinates yl and yu, what are all the horizontal lines that lie between them? And those are the ones that are going to intersect, and you report them. So you report all these intersections, and eventually you will have all the intersections reported. Okay? Yeah.
How are going to know which ones to remove if we're only keeping track of the x? So if we're going to remove, how do they know?
Well, there are two different data structures. One is the event queue. Event queue is x coordinates.
Okay.
The other data structure is the red-black tree of active horizontal line segments. This is all y coordinates. There is no x here.
But the queue tells it what to remove, right?
So along with each x value here, you will have information saying, oh yeah, this x coordinate is the left endpoint of horizontal line segment number 17. Okay. And same thing with the vertical line. So it'll tell you, oh yeah, this is the x coordinate of vertical line number 43.
So there's a little bit more than that.
This is a little bit more than just the x coordinates. Okay. Same thing over here. I am, remember this is a data structure, so therefore I need a key value because it needs to keep things sorted. And the key value is going to be not the x coordinate, but the y coordinate. But along with each y value, I will also say this is the y coordinate of horizontal line segment number 9.
Okay, that makes sense.
Okay, and so each of these will be connected to a list of horizontal line segments. And so therefore, from this y coordinate, I can figure out which horizontal line segment I'm talking about. Yeah.
Let's say I just wanted to know the number of intersections. Like
Right.
I didn't care about this. I can use a range.
Yeah,
tree.
then the range tree can then solve this in just log n time. You don't need this number of intersections. So that's the advantage.
But does red-black tree have this?
Yeah, you may have to write that code, but there is something called I discussed this in class. There's something called OS rank and OS select. So in a dynamic data structure, I can give you any value here, and it'll tell me what is its rank in the list. So that requires a little extra work, but it can be done in log n time. So if it is between y3 and y4, all I have to do is to find the rank of this and the rank of this, and I'd know where it's coming. And if YL falls somewhere here, we know it's between ranks 1 and 2. If this guy falls here, we know it's between ranks 3 and 4. So all I have to do is to subtract 3 minus 1 it has to intersect two things, and that's all you report. So I can do all of that in log n time. But if I actually have to report which ones it intersects, that'll take me extra time, because I don't know how many there will be in between. Right? So that's pretty much the whole algorithm. There are a few pieces that seem to be hidden over here. The hidden stuff is actually not that complicated. The first sentence is the event queue. That's simply a sorted list. That just requires calling some sorting algorithm. You can call merge sort or heap sort or whatever sort, and you would have a sorted list of x coordinates. That's easy to do. This data structure, as I said before, it's a standard package. If you're writing Java code, this is going to be readily available. But you have to make sure that your operations that you want are available with it. Insert and delete are standard. In red black trees, you'll find them. Search is standard, but here you may want a little bit more than search, because you have to know it's between what and what, right? Or you may want to add to this a what's called as a range query. So I'm going to add that here and say range query. And there are actually two kinds of range queries. One simply asks how many values are between are in this range, and the other asks to actually report the items that are in this range. So if you only want the number, that's log n time. If you want the actual items, it's log n plus the number of items. And so with these pieces, this whole thing can be coded up. So if you're going to discuss this on Tuesday, this is actually writing up 4 different pieces, and it should be fairly easy to do. Yeah. Any questions? You're all good? Right. The next variant of this problem makes life much more complicated. What do you think we do? How do we make this problem complicated?
The lines are not horizontal.
The lines are not horizontal or vertical. If they're not horizontal or vertical, what the heck are we going to do? Because you don't have the line segments, here it was nice because for every vertical line there was only one x coordinate. For every horizontal line there was only one y coordinate. Made life so much easier. This data structure only dealt with x coordinates. This data structure only dealt with y coordinates. All that was clean. Life was simple. We could actually figure this out, right? So this is called the general line segment intersection. We'll assume that none of the line segments are horizontal, none of them are vertical.
Do you have to maintain an active list for vertical line segments?
Well, I just told you there are no vertical line segments.
Sorry. Oh. Not on
Yeah.
I was thinking more like greater than 45 degrees or 45 degrees, but yeah.
So earlier we knew that a vertical line segment can only intersect with horizontal ones. So we knew what to search, where to search. Here, any line segment could intersect with anything. And let me draw a picture somewhere. Let me see if I have a picture. I don't want to show you those pictures. They give away too much. So here they are. Looks nasty, huh? And your job is to report all these intersections. And you'd like to do it in roughly the same amount of time. By the way, the time complexity of this other algorithm was n log n plus k, where n, of course, is the number of horizontal and vertical line segments, and k is the actual number of intersections. Okay? You'd like to do it in roughly the same amount of time over here. And it turns out that most of the things we learned over here, we can apply it here, even though life is not so straightforward. Okay? And we're going to still maintain an event queue. An event queue is going to be only x coordinates. And we're going to keep track of active, not horizontal line segments, just active line segments. Because at any given time, I have a vertical line segment, right? And I know which line segments are active, right? Because here, anything that it intersects is an active line segment. And we're going to keep track of this. Yeah?
So, I'm just ideating. Instead of having single y, will you maintain tuples of y?
Yeah, so what I actually put in there is a good question, and I'll give it to you in a few minutes. Clearly, I can't keep a red-black tree of y values, because there is no y value. This thing is either going up or going down, who knows?
If you write a custom comparison function between tuples?
Yeah, keep thinking. You're pretty close, but let me cater to everyone here and make sure that they're understanding this. Okay, so one of the challenges is, what are we going to do here? Because it's not y coordinates, and over here we don't have two kinds of x coordinates. We only have one kind of x coordinate, right? It's either the start endpoint or the right or the end. Sorry, what am I saying? Either the left endpoint or the right endpoint of any line segment. That's all we have. Okay, so let's see how these things change. Any questions about what we did earlier? We're good so far? And how am I doing the time? Okay, 4:15. Perfect. Yeah. So, yeah. So let's change some things here. We're not going to have x coordinates of vertical line segments. We're not going to have x coordinates of horizontal line segments. Instead, we're going to do, we're going to just call it left endpoint and right endpoint. X coordinate of left endpoint and x coordinate of right endpoint. And it's not of horizontal line segments. So I've just changed it so that I only have left endpoints and right endpoints. Okay, here is left and here is right. And whatever is the x coordinate of that, that's what we are interested in. So here, the event queue will contain what? It's going to be easy for you to see. It's the x coordinate of all these guys. These are all left endpoints, right? Oh, am I missing any left? Oh yeah, this guy here. These are all left endpoints, right? And then I have right endpoints. The right endpoints are this guy here, this one here. And yeah. So these are all the x coordinates of interest. This defines my event queue. Clear? So I took the x coordinates of anything, whether it's left endpoint or right endpoint, took those x values, sorted them, and stuck them into a queue. That's still my event queue, just like before. Only thing is, these are not horizontal lines anymore, or vertical. So that takes care of the event queue. I still have to tell you about this guy. Well, I also have to tell you the other thing that's different here is that the intersection doesn't happen at just these event points, right? This intersection is between this event point and this event point. That's not good. You can see here, this guy here is somewhere there. It's not at this endpoint. It's not at this event point or this event point. It's somewhere in between, right? So it's kind of hard to figure this out. So even reporting an intersection point is going to be a bit more challenging this time. So we have to still decide what is it that we are storing here. I told you that we are going to keep track of active horizontal line, active line segments. So remove the word horizontal, right? Which means that if I hit this guy here at this point, it's the start of a line segment. So let's call this as line segment 1. So I'm going to put this line segment into my queue, into my data structure. If this is line segment 1, L1, somewhere I'm going to have L1. Then I hit this guy here. This is, let's call this L2. Somewhere here I'm going to store L2 when I hit that event. Then when I come here, it's L3. So somewhere here, L3 becomes active. Then I will hit this point here. You'll see that L1 stops becoming active. So I'm going to remove L1 from here. Okay. Then I come here where, let's say this is L4. L4 becomes active. Then I go to the next guy here, and L5 becomes active. Then I go here, and L6 becomes active. And then I go here, and L3 stops being active. And then I go here, and L2 stops being active. Then I go here, and L6 stops being active. Then over here, L4 stops being active. And finally over here, L5 stops being active. So I've just told you how the data structure will change. It will keep track of active line segments as we sweep from left to right. Right? But what happens at each of these points is what we discuss next. Okay, so when we get here, we know that L1 gets put into this data structure. Then when we get here, L2 gets added. So let's restart this process and think about it again. Yeah, I can remove this here and redo that. So here's my data structure. So far, I have added L1 to this. So let's assume I'm here, and L1 just became active. So it's somewhere in my data structure. Then comes L2, and I need to add it to this data structure. What I'm going to figure out is I need to order all the line segments that I have there with respect to the line sweep. What does that mean? It means, imagine my vertical line sweep. I don't have another color, unfortunately, but imagine that I have my line sweep, right? I've just crossed L1 and I added that. Then I've come to L2. I want to add that. However, look over here. If you look at this vertical line segment at this point, what you'll see is that L2 is below L1, right? So according to this line, the perspective of this particular vertical line, L2 is below L1. So I'm going to keep track of which guy is below which other guy. Okay, So I don't care about their precise positions. I don't care about their y coordinates. I just need to know that L2 is below L1. Okay? And I'll tell you more about exactly how it's organized in there, but let's try and move forward here. Later, when L3 becomes added, where does L3 go? It's the top, so it should be on the right of L1, right? Then L1 goes away. Well, fine, L1 goes away. We'll just get this out. Then L4 comes in, and L4 is below. Oh wait, so yeah, bunch of things are happening here, and I have to stop and tell you what's happening. Let me go back to the start. I have L1, and I told you that L2 is below L1, right? As soon as I put it in there, I'm going to look and see whether L2 and L1 intersect. And over here, does L2 and L1 intersect? Yes, it does. It does intersect. And we know we went through this lesson with how to find the intersection point between two line segments. So we find that intersection point, and at this point, this is an interesting x coordinate. I'm going to add that to my event queue, because this event queue keeps track of all interesting x coordinates. Okay.
You have to add it in a sorted.
So I have to add it in a sorted way. So this is not going to be a dump queue, but it's actually going to be a data structure. But we are only going to do we're only going to do inserts, and we're just going to go from left to right. So we are also going to add x coordinates of intersections. And remember, these are future intersections. Okay? So anytime I add a line segment, I am going to check whether I won't check the intersection with everything there. I'll explain that in a minute. But for now, I have only two things. So I'm going to check for the intersection, and whatever that x coordinate of the intersection was, I'm going to add it to my event queue, so that later, when I hit that point, I have to do something about it. And I'll tell you what that is. You had a question?
I was going to say the assumption is that intersections are always next to each other.
Yes, and that'll become clear as we go along.
What did you say? The assumption is that?
The assumption is that there is an ordering of things here.
Okay.
Well, as we add more things, it'll become clear. So give me just a couple of minutes. I think it's a little early to talk about that. So I checked whether L2 and L1 intersect, and yes, they do. Instead of reporting it, I just put it on the event queue. Okay, with a little note saying, "Oh yeah, this was actually the intersection between L1 and L2, and it happened at this x coordinate." So I'm not yet reporting it. I'll report it when I get there, but I know it's a future event. It's interesting, and what is much more important is the following: at this intersection point, the ordering between L1 and L2 flips. Here, L2 was below L1, right? But as soon as it intersected, L2 became above L1, right? And so we're going to do something, because remember, we're keeping the ordering of these line segments, and the ordering are according to a vertical line sweep. All right, and all that will become clear a little bit later. So we just add that event over there, because there is work to be done when we hit this particular event, and so we put that into the event queue. All right, so we've just finished L1 and L2. We got here, we are going to add L3, and we said that L3 is above L1. So L3 gets added over here, and so therefore, we're only going to check the intersection of L3 and L1 If there is an intersection, we'll add it to the event queue. We won't worry about L3 and L2 because they're not next to each other. So L3 and L1 don't intersect. I don't have to report anything, which means L3 will always be above L1 since it never intersects. To start with, it was above, and they don't intersect. So for the lifetime, we don't have to care about that intersection anymore, and L3 will remain above L1. Great. So L3 got added. The next event turns out to be the intersection between L1 and L2. When that comes up, we're going to report it as a major event and say, here is the first intersection I've found. But more importantly, at that intersection, L2 and L1 had to be flipped. So now I am going to go over here and change this to L1, L2.
And now you check again for each other.
So what happens is anytime you flip two things, you have new neighbors for both these guys. You have to check their intersections. So therefore, if this was my list over here, and if these two guys got flipped, yeah. Remember, before they intersect, they must be neighbors. Otherwise, it's not possible. So if these two guys get flipped, we look at what are their neighbors, and now we check the intersection between this and this and this and this. Is that clear? And if they intersect, we add it to the queue. And remember, early on, we never checked the intersection between these two, so that intersection point, if at all it is there, is going to be added for the first time. And same thing with the other one. Yeah?
You said that if they intersect, they should definitely be neighbors, right?
Yes.
But if they are neighbors, there is no guarantee that they will intersect.
Correct.
How are you saying that when the converse is not true, how are you saying that?
So I don't have to report it. That's all that I care about. I care about reporting every possible intersection.
No, I'm saying, how are you claiming that every intersection is only caused by two neighbors?
Yeah, you'll see that. At the point that they intersect, they have to be neighbors. This is my claim.
At the point they intersect.
Right.
Okay.
If there was something else in between, they're not going to intersect right yet. So for instance, think about it this way. These two are intersecting, right? Right before intersection, this guy was above this and they were neighbors. If there was something else, how is that going to happen? That's going to happen because there was something else here, right? Somewhere there. Did that cut it before or after?
Before.
In this case, it's before. It could have been after. But the ordering got messed up. But this intersection here would have been processed, and again it would have gotten flipped, and they would have become neighbors. Does that make sense? So whatever it is, they're going to become neighbors just before that event actually occurs. Should I expand that picture? Did that make sense?
Yeah.
Yeah? You got it?
Is there a way we can prove it?
Yeah, you can prove it just by saying that if this is the intersection point, one line must come from above, one must come from below. If they're not neighbors, there must be a third one. Either the third one also intersects at the same point, where, by the way, we are disallowing that. We don't want messy things, so we'll assume that only two lines intersect at a given point. If that doesn't happen, either it must intersect the lower line before or the upper line before or after. If it is, well, it's not possible it's after, because this point is the intersection of these two. So it must be intersecting either this line or this line first. Whichever it is, that will give you an event, and these two would get flipped. So that means at that intersection, the ordering was not the black guy between the other two blue ones. That's all we are contradicting. Okay? Questions? All good? All right. So we just added L3. We checked whether it intersects L2. It does not, so we move forward. L1 finished, so I'm going to remove L1 from this list. And actually, when you remove, there's a little work to do, but maybe it'll show up in another example, and I'll tell you that. In this case, it turns out to be trivial. So what's next? So when we flipped L1 and L2, we looked at the intersection between L2 and L3, and there was one. And so this event gets added to my data structure, my event queue. So this guy here is another event that'll get added. And it turns out that that is the next event that'll come out of the event queue because you added it before you got there. And when that happens, L2 and L3 have to be flipped because L2 is now above L3. So beyond this point, L2 is above L3, right? So we change this to L2 and L3. L3 and L2. And there's nothing else to be checked on either side, so we continue, right? What's next? The next thing is L1 goes away after that. So anyways, L1 is gone. Then comes L4 start, and L4 is below L3. So L4 is going to be here, right? Then we have L5 starting, and L5 is above L3, above L2. So L5 is here. By the way, when you added L4, you check whether L4 and L3 intersect. If so, we add it to the queue. We check if L2 and L5 intersect, add it to the queue. Do they? Well, L2 and L5 does, so we have to add this particular x coordinate. Do L3 and L4 intersect? They do, and we have to add this intersect. So there are more interesting events that get added, and when they come, we'll do something about it. Okay, and you'll see what we do. So we have now added L5, and the next thing that happens is the intersection between 2 and 5, right? And remember, 2 and 5 are neighbors, which is what we convinced ourselves should happen. When they intersect, what happens? You flip them. So now this becomes L5, L2, and we will report the intersection between 2 and 5. So L5, L2. And now, because we flipped, we have to check whether L5 and L3 intersect, and they don't, so nothing to do over there, right? And L2 doesn't have a neighbor, so I don't have to check anything else. Are we good? So this data structure maintains all your line segments in the order in which they will be seen by any vertical line segment, not by a y coordinate. Okay? Right. And now we keep going. Where are we now? I forgot where we are. We're at L5. So by the way, we've reported L1 and L2, whatever that was. And then we reported L2 and L3, right? And then we reported L2 and L5. These are the intersections we have reported. Okay? And now we are past this point, and we got to the start of L6. L6 is way below even L4, so L6 will get added over here. And we'll check whether L6 and L4 intersect, and they do. And so we're going to add this guy to our event queue. L4 and L3 also intersect, and that was this, yeah. So I just added L6, right? And anyways, yeah, that event would have. So I've added these events here already, And so the next thing that I will encounter is the intersection between L4 and L3. And when I hit L4 and L3, these two have to be flipped. So when I flip this, this becomes 3, this becomes 4, and I will check whether 3 and 6 intersect. I'll check whether 4 and 5 intersect. If they do, they go into the queue. In this case, it would be 4 and 5. 4 and 5 do intersect, so that comes here. And we also check if 3 and 6 intersect. 3 is here, 6 is here, so we get that guy here. Okay? It's getting a little messy here, but you get the idea, right? So we are now ready to write the algorithm, more or less. We know all the pieces, but I haven't quite told you one important piece. I haven't told you what it means to organize this data structure. How do we decide something is above or below? That turns out to be quite simple. Every line segment can be written down as an equation of a line, right? So each of these, not only do they have left endpoints and right endpoints, you also have y equals mx plus c, right? So we have two line segments, y equals mx plus m1x plus c, c1, and y equals m2x plus c2. So think of these as two line segments. The lines corresponding to two different line segments. We want to know which one is above which. But that's easy because we are dealing with a vertical line, and a vertical line has an x coordinate. So we plug in that x coordinate. What do we get? If we plug in an x coordinate, we'll know what the y coordinate is. We know m1 and c1. We know m2 and c2. So we plug in the x coordinate in both of these, figure out which one is larger. That'll tell you which one is above which one. Very, very simple. So when we sort, it's the comparison operator that needs to be changed. The comparison operator is going to take an x value and use that to decide which one is above which one. And whichever is above the other at one point will remain that until those two intersect. Until then, nothing will change. One of them will remain above the other. And that's all you care about. So that's how this gets organized. In a red-black tree, you're always checking whether A is less than B. Here, we're going to use an x coordinate to figure out whether the line is above or below. Is that clear? Yeah.
You said the points of interest is when two lines intersect. What if three lines intersect?
Yeah. So we're going to assume that doesn't happen.
Also collinear.
It's called a degenerate case. So in order to prevent that from happening, there are various tricks. You add an epsilon value to everything, or add either plus or minus epsilon to things, or add a little noise, so that three lines never intersect at the same point. Okay.
Also collinear line.
Yeah, that's right. We could have two line segments that are sitting on top of each other or something. So there are lots of degenerate cases. There are simple ways to check them. Collinear lines, you just have to find if two things have the same slope. That's easy to figure out. And the degenerate case where you have three lines intersecting at the same point, you could just ignore that and assume that one happened just before the other, and so it doesn't matter in what order you process them, you will still get all the intersection
But
points.
wouldn't the number of intersections increase by 1?
Well, no, because if three lines intersect there, you could just imagine reporting all the intersections.
Oh, okay.
Right.
But the number of points is lesser, right?
True. Those are degenerate cases, and they have to be dealt with in some special way anyways, so you would end up spending a little more time there, and that's okay to do at least in this context. Are all the pieces clear? So the event queue is more or less the same, except that we only care about left endpoints and right endpoints. But later on, we'll also have x coordinates of these intersections that will get added there as possible events. Then we will process the events from left to right, except that this event list is somewhat changing. There are things that keep getting added to it. But there are three kinds of events now. One is it's the left endpoint, the other is it's a right endpoint, the third is it's an intersection point. If it's a left endpoint, we are adding an extra line to our data structure. If it's a right endpoint, we are removing a line from the data structure. And if it's an event, we're reporting it. And we are doing a flip of something. In each case, if we have a list, and if we insert a new point, this guy is going to now have two new neighbors. We have to check for intersection between those two new neighbors and add it to the event queue if it's needed. If we are deleting this, then we've already checked the intersection between these two and these two, but now these two become neighbors because you've just removed something, which means you have to check the intersection of those two guys. And that's happening because you have something like this, and this guy just ended here, right? As soon as this ended, now these two have become neighbors, and they may intersect, and you have to check this. So we go and check this, and if needed, we'll add it to our event queue. So during inserts, we have to check the intersection of its two new neighbors. When deleting, we have to check the intersection of the two things that become neighbors because this guy got removed. And then there is another possibility, which is if you hit an intersection point, you're flipping. And so there again, you have to check the two new intersections between the two pairs that are formed. Is that clear? Each of these could generate a new event that goes in there. They're all events that are happening later. They're not events that happened in the past, so I don't have to worry about them. Okay? And I told you how we're going to order these line segments. They're going to be based on the y coordinates at any given x coordinate. So you can still use a red-black tree. All you have to do is to change the comparator operator in the red-black tree. Very, very simple. Right? So even though it looks messy and complicated, it turns out that with minimal amount of work, we've figured out how to deal with this. There is one other piece, and that is for two line segments to figure out the intersection point. And that involves solving a simultaneous equation, and you guys know how to do this. Right? That's all there is to this problem. And time complexity doesn't change. There is a bit of extra work in trying to figure out the intersections and adding them to the queue. But the queue here, the number of things you'll add there is going to have k, which is the number of possible intersections. So you will get there's some trick here to figure out how it's going to be n log n plus k, because it looks like it's going to be n log n plus k log n. You have to worry about this a little bit more. Those are algorithmic tricks that you're not going to use in your programming. So we'll skip that discussion. Any questions? It's a really, really nice problem where all the pieces are elementary, right? You're using a simple sorted list here. You're using a simple red-black tree here, and what's called as a range query. So if you start with discussion of a range query, you can then understand all the pieces and write them together. So let me go and spend 3-4 minutes on the range query problem. How am I doing with time? I am past time. I have, well, let me quickly say this. A red-black tree maintains a set of values in roughly in sorted order. A range query will give you two values and says, tell me all the values that are between A and B that are in this data structure. And as we discussed earlier, there are two kinds of problems. One problem, you want to know how many values there are between A and B, and the other has which values are between A and B, and to report them. Both of these have slightly different time complexities. In one of them, you start at one and then you do a in-order traversal until you get to the other one. So that's easy. And in the other one, you have to use this rank data structure to figure out how many are between A and B. And the rank is something we discussed in class, so I'm happy to discuss that another day. It's actually a really nice problem. But our time is running out for this semester, and next semester, pretty much early, we have a competition. So we need to figure out how to ramp up our level of competency here. So perhaps very soon I'll start on dynamic programming and start to look at some difficult problems there. So perhaps next week we'll start with dynamic programming. This range search is a good problem, so maybe we should find some problems for the mock competitions and have people play with this. Give them some easy problems with range search, and then we can get to line intersection. That's what I would suggest for the beginners. I didn't show you these pictures here. You can see here what happens. G ends before E and F intersect. So the moment G ends, it gets removed. Now E and F become neighbors, and so you check when their intersection is, and then this point gets added to your, somewhere here the intersection gets added to the queue. And then after the intersection, they flip the order. F becomes higher than E, and then when I comes in, that gets inserted between F and E, and now you have to check for intersections between I and E and I and F. Yeah, so those are all things that happen. You can look here what happens as you sweep the line. Over here, it's only A. Over here, A is above B. Over here, A is above C above B, right? Over here, it's D followed by A followed by C followed by B. So when you insert them, you have to know in what order they will show up. So you get to see what this data structure looks like. Here, it's just shown as a list, but actually you store it in a red-black tree. And then you can see here when the first intersection happens, the order will start to flip and do interesting things, right? But until then, fairly straightforward stuff happens. Yeah, so you have two things that are going on, and all that is explained. Here's the actual final code. So you sort the endpoints. Remember, you have to build this queue data structure. So you sort everything by x coordinates of the left endpoint and right endpoint. To start with, there are no intersection points. So these guys, there aren't going to be any intersection points that you're adding. But then, as you start to process things in the sorted list of endpoints, there are two possibilities. One is it's a left endpoint. The other is it's a right endpoint. There's actually a third case when it's a intersection point, but that stuff is included in here. So they've kind of done something else. Wait, where is it? Yeah, you need a little bit more than this. This is from the text. I'd have to look at why it doesn't include that third case. But you see here when you insert something, the thing that's above and below it, you have to check for intersections and add it to your queue. And when you look at the right endpoint, you're going to delete something. Then you take the above and below and see if they intersect. And if needed, you'll add it to the queue. So that's roughly what we discussed. It is missing some things. I'd have to look at it again and see why it's missing that. Okay. Let me stop here. Any questions?